Sorry about having to split the video into another part. I had a small technical difficulty. Let's begin again. We were looking at calculating the number of propane molecules in 74.6 grams of propane. If I have that 74.6 grams to start with, I then have to put in my conversion factors. We have done our calculation to show that there are 44.11 grams of propane for every 1 mole of propane, and then we know from Avogadro's number that there are 6.022 times 10 to the 23rd propane molecules for every mole of propane. This gives us an answer of 1.02 times 10 to the 24th molecules of propane in 74.6 grams. Now we need to calculate the number of oxygen atoms in 26.5 grams of lithium carbonate. Now, I'm going to pause for a few minutes and allow you some time to do this calculation on your own. Okay. I'll give you some hints, and then if you need help getting the answer, you can post on the discussion board. Remember, you need to calculate the molecular mass of lithium carbonate. Make sure you count up the proper number of lithiums, the proper number of carbons, and the proper number of oxygens. Once you know that mass, that's how many grams of lithium carbonate there are for every 1 mole of lithium carbonate. Once you know the number of moles of lithium carbonate, then you can figure out how many moles of oxygen there are in every molecule of lithium carbonate. That is tricky. Once you know how many moles of oxygen you have, then you will put in the molecular weight of oxygen for every mole of oxygen and Avogadro's number. Take some time to try to figure this problem out. It's the trickiest one in the group, and see if you can do it. Alex will help you, as well as any other of the items in the activities. Now I want to switch gears a little bit and talk about solutions and mixtures. A solution is a mixture of 2 or more substances that are dissolved in one another. The solute is the substance that is present in the smallest amount. The solvent is the substance present in the largest amount. If the solution is called an aqueous solution, that solvent is water. So in this picture, we're dissolving salt into water. Salt is the solute and water the solvent. There are lots of types of ways you can make a solution. Every single one of these is considered a solution, even though you most typically think of putting a solid in a liquid. You can dissolve a liquid in a solid, or a solid in a solid, or a gas in a liquid. So be careful on that definition. Solubility refers to the maximum amount of solute that you can get into a given amount of solvent. Usually we'll say this as the amount that dissolves in about 100 grams of the solvent. If it contains less than the maximum, that solution is considered unsaturated. If it contains the maximum, it's called saturated. You can increase the temperature of something, basically heat it up, to make more dissolve. We like to talk about how much chemical is in a solution and use that to do chemical math. The most common unit that we use in chemical math for referring to how much solute is in a solution is called the molarity. And that resembles the number of moles of solute for every liter you have of solution. It's capital M for molarity equal to moles over liter, as shown right here. So if a solution is known to be 6.0 molar hydrogen chloride, I know that it has 6 moles of hydrogen chloride in 1 liter of solution. And these are the conversion factors as they would be written. If a solution is 0.2 molar in sodium hydroxide, then I know it has 0.2 moles of sodium hydroxide in every liter of solution. I will make a solution just as shown here. I would put in the amount of solute I need. In this case, I'm making a 1 molar solution of sodium chloride. I will measure out a mole of sodium chloride at 58.5 grams. Put it in the flask. This is a volumetric flask. I'll add water to dissolve it, fill it up to this line, and mix it. And I will have a 1 molar solution of sodium chloride. And I use this to do calculations. I would like to know the calculated molarity of a solution that has 12.5 grams of sulfuric acid in 1.75 liters of solution. So I know the definition of molarity is moles of my solute, sulfuric acid, over liters of solution. I have 12.5 grams of sulfuric acid, and I have 1.75 liters of the solution. I must then use my conversion factors, add up the weight of sulfuric acid from the periodic chart, just like we did before, 2 hydrogens, 1 sulfur, and 4 oxygens, and that is 98.1 grams in every 1 mole. These grams here will cancel out with these grams here, and I will be in moles of sulfuric acid over liters of solution, which will be molarity. The molarity of that solution is 0.0728 molar. So do the same thing for this. Determine the mass of calcium nitrate that is required to prepare 3.5 liters of 0.8 molar calcium nitrate. I'll give you a few seconds to do that problem. Or pause at this point and work out the problem. Okay, hopefully you took some time to work out the problem, but here's the answer. If you have 3.5 liters of 0.8 molar calcium nitrate, you have 3.5 liters here. Its conversion factor is 0.8 moles of calcium nitrate per liter. Liters cancel, leaving you in moles. You know the formula mass of calcium nitrate because you've calculated that before, but you can calculate it again. Remember, there's 6 oxygens and 2 nitrogens and 1 calcium. Makes 164 grams. This mole of calcium nitrate here cancels with this mole of calcium nitrate here, leaving me in grams of calcium nitrate if you follow the units. And that is 459 grams of calcium nitrate that are required to make 3.5 liters of 0.8 molar calcium nitrate. Okay, now that we've looked at concentrations, it's now time to look at chemical equations. Chemists write chemical equations to show what is happening in their chemical reactions. They always are of the same style. Reactants are on the left, products are on the right, and we say the relative amounts of each one using the coefficients. Here's a visual representation of some reactions. This is a reaction between methane, CH4, and oxygen to make carbon dioxide and water. CH4 methane is drawn here, 2 oxygen diatomic molecules here, making the products CO2 and water. And you should be able to count to see that all the hydrogens that are over here end up over here. All the oxygens over here, there's 4 of them. You got to have 4 of them over here. 1 carbon, 1 carbon. That's how you balance the equation. Here's another version of a chemical equation. This one is for the reaction of iron oxide with carbon monoxide. With heat, the little delta there on top of that arrow means heat, to make iron solid and carbon dioxide. The iron 2 oxide reactant has 1 formula unit or 1 mole of iron 2 oxide, and there are 3 formula units of carbon monoxide, or 3 molecules or 3 moles of carbon monoxide. The arrow sign means yield, and then we make 2 atoms of iron, or 2 moles of atoms of iron, and 3 molecules of CO2, or 3 moles of molecules of CO2. We also put in the states of matter, solid, gas, for each one. Here are some symbols that you will see on chemical reactions. The plus sign to add them together, the arrow to show the separation between the reactants and forming the products, delta for heat, SLNG for solid, liquid, and gas, and AQ for aqueous for things dissolved in water. You have to remember from way back now that we have the law of conservation of matter. We cannot destroy any atoms. Everything must balance on one side and on the other side. So you have to count them. The only way that you're going to get really good at this is to practice this. There are problems in this PowerPoint as well as on the other activities. Here are the general steps for balancing an equation. Make sure the formulas are correct. I will not typically have you write a formula, so that will be okay. Should be fine. Determine if it's balanced. You always count the numbers from on one side and on the other side. See if they're the same. Balance one element at a time, picking one, and saving oxygen and diatomics for the last. And then check again to see if it's balanced. So let's look at some reactions. The first kind of reaction that we'll talk about today are the combination reactions. This is when two or more substances combine to form something else. There are three types. Two elements react to form a new compound, an element and a compound react to form a new compound, or two compounds react to form another compound. Here is an example. Sodium plus chlorine makes sodium chloride. Magnesium plus oxygen make magnesium oxide. Aluminum plus bromine make aluminum bromide. But you will notice that these are not balanced equations. In this one, we have two chlorines here, but we don't have two chlorines over here. If I put a 2 here, which you should do on paper, write this out on paper. If you put a 2 there, you now have two chlorines, but you do not have two sodiums on this side. So you will need to put a 2 here and a 2 here. Write that on paper and confirm it for yourself. What about for magnesium oxide? Well, same sort of practice. If I already have two oxygens here, I've got to get two oxygens here. So there will need to be a 2 over there on the magnesium oxide. Once I do that, I will now have two magnesiums on that side, and I will need another 2 over here. This one's a little more complicated because I have 3 bromines over here and only 2 on this side. If I multiply this side by 2, that would give me 6 bromines on that side. And I could put a 3 here to give me 6 bromines on this side. I would then have 2 aluminums on this side and need a 2 for the aluminum on that side. Here are some more for you to practice. Do the same thing and make sure that you can get the right answers. Check your answers with one of your classmates, or if you have a problem with one, please contact me. The next types of reactions are called decomposition reactions. These occur when one compound decomposes or falls apart to make either two elements, one element and one compound, or 2 or more compounds. Here are some examples. N2O with heat will decompose to nitrogen and oxygen. Silver bromide in the presence of light will decompose to silver and bromine. You try to balance this equation. If you do not think that you're getting the right answer, or if you are struggling, please come to the virtual office hours or ask a classmate or post in the discussion boards so that everyone can see how to do the problems. Here are a few more decomposition reactions. Try the same thing. Some of them are easy, some of them are not easy. Check to make sure they're balanced and practice, practice, practice. Displacement reactions occur when one element displaces another element from a compound. There are many types. We won't go into all the types, but what I want you to note is that this is a case where these are swapping partners. First, initially, the silver and the nitrate are partners, and copper is by itself. After the reaction, copper is now switched with nitrate, and silver is by itself. Same thing here, aluminum by itself, sulfuric acid, the hydrogen, and the sulfate together. Over here, the sulfate has gone to the aluminum, and the hydrogen is by itself. The flop happens in the chlorine reaction with sodium iodide as well. Make sure that these are balanced. They should have the same number of atoms on every single side. Count them up, Write them down and see if you can get the right answers. Here are some more displacement reactions. These are actually double displacement, as you can see that both of them are switching partners. The calcium chloride and sodium phosphate, the calcium ends up with the phosphate and the sodium ends up with the chlorine. Happens in both cases below as well. Take some time and practice balancing the equations. Always count them up on each side. If you're struggling, please see me. Here are the overview reactions of what we just talked about. These are the symbol forms for those reactions. Finally, we're going to look at a couple more calculations based on chemical equations. When I have a chemical equation and I have a certain amount of a reactant, it can react with a certain amount of another reactant to make a certain amount of product. And that's what I use in this graphic. Everything gets converted to moles. That is the main thing you should remember. Grams of whatever compound you want to start with, convert it to moles. Grams of some other compound, convert 2 moles or from moles to grams. We always do all of our reactions on the basis of moles, not on the basis of grams. So for example, iron oxide, iron 2 oxide, iron 3 oxide, plus carbon monoxide yields iron and CO2. We want to know how many molecules of carbon monoxide are required to react with 25 units of iron oxide, iron 3 oxide. Well, if I have 25 formula units of iron oxide, and I know from this equation 1 unit reacts with 3 units, then I would say 1 formula unit and 3 molecules. That means I need 75 molecules of carbon monoxide for every 25 molecules of iron 3 oxide. Let's go some more. How many iron atoms can be produced by the reaction of 2.5 times 10 raised to the 5th power? This should be raised up right here. Formula units of iron oxide. Let's see. If I have 2.5 times 10 to the 5th formula units of iron oxide, 1 formula unit of iron oxide contains 2 iron atoms. That means I have 5 times 10 to the 5th iron atoms. Now, what mass of carbon monoxide is required to react with 146 grams of the iron 3 oxide? If I have 146 grams of iron 3 oxide, I calculate its formula weight, 159.7 grams for every mole. I know there's 1 mole of iron 3 oxide to 3 moles of carbon monoxide, and I know that there's 1 mole of carbon monoxide containing 28 grams of carbon monoxide to give me an answer of 76.8 grams of carbon monoxide. Be sure that you follow through the canceling of each of these units. Here's another example. What mass of carbon dioxide can be produced by the reaction of 0.54 moles of iron oxide with carbon monoxide? I start on the left-hand side of the equation, 0.540 moles of iron oxide, iron 3 oxide, 1 mole of iron 3 oxide to 3 moles of carbon dioxide that is produced on the right. 1 mole of CO2 weighs 44 grams to give me 71.3 grams. Now you might be a little confused by that one, so I'm going to show you the reaction again. 1 mole of iron 3 oxide makes 3 moles of CO2. Okay. 0.54 moles of iron 3 oxide. 1 mole of iron 3 oxide reacts to make 3 moles of CO2, and that's how you get the 71.3 grams. Okay. What mass of iron oxide reacted with carbon monoxide if the carbon dioxide produced had a mass of 8.65 grams? Try this problem, pause the presentation, and try to do as much of it as you can. Now that you're back, here's the worked out problem. If we make 8.65 grams of CO2, We know its formula mass, 44 grams in 1 mole. 3 moles of CO2 relate back to 1 mole of iron 3 oxide. 1 mole of iron 3 oxide weighs 159.7 grams, which means we had to start with 10.5 grams of iron 3 oxide. Finally, what mass of carbon monoxide is required to react with 146 grams of iron 3 oxide? You should be able to do this one as well. It might take some more practice, but I have high hopes that you will understand most of these problems. Here it is worked out to give you the 76.8 grams of carbon monoxide. I know that was fast. There's lots of other review in the work for this week, so don't get discouraged if the math seems kind of hard for you. Keep practicing.